All right, welcome back everyone to another PhenomeForce workshop. We're got an exciting interactive workshop for today. I'm Claire Gahagan, I'm with Agriculture Canada, and I'm one of the PhenomeForce reps today. And I have Jennifer with me here today. She's going to help me co-host. So this workshop is part of the Drone to Phenome collaboration with PhenomeForce, and we're looking at principles, protocols, and pipelines for drone phenotyping. So PhenomeForce, if you're not familiar, we are a community looking to connect people working in phenomics and empower early career researchers by giving them an online library of resources and training in phenomics. So we have workshops like today's where we focus on established phenotyping pipelines and showing people how they can use the tools and potentially bring them into their own research. So if you are interested in becoming involved with PhenomeForce, we have a Slack channel, and you can email us to be part of that community if you'd like to join. And the information on that is below. Also, if you want to get emails about future workshops, we have a registration link below as well. And for the drone to phenome background, I'm going to add in Max Feldman.
Good morning, everyone. Yeah, this is kind of an exciting initiative by the USDA Agricultural Genomes to Phenomes project. Basically, this is just a pilot project, kind of trying to identify bottlenecks in adoption of drone phenotyping, and also identifying protocols that are easy for those of us that don't have a lot of experience doing this to deploy within our research programs. And so I'm just excited to hear what Dr. Kruase is going to share with us today.
Yeah, and you guys have a website that'll be coming up shortly for the Drone to Phenome project, right?
Yes, that should be coming live sometime in the next month or two. Yeah.
Great. So if you're watching this after the fact, we may have that information added into the description below as well. So for today's workshop, we have our wonderful speaker, Margaret Kruase, and she'll be talking to us today about predicting grain yield with aerial hyperspectral reflectance data. So without any further ado, Margaret, and when you're ready, I'll add your screen onto the stream if you want to get your R started up, or your presentation started up. Margaret actually has an interactive section today. So if you're interested in following along, there's a link to Google Drive below, and that's where we have the R script and the CSV you'll need to do today's workshop. Alrighty. Good luck today, Margaret.
Okay, can you see my screen?
Yes, it looks good.
Okay, great. So thank you for having me. This is a really exciting opportunity, and it's great to be with this group today. I'll be introducing this in the context of wheat and grain yield and hyperspectral reflectance, but really what this is about is kind of a statistical method to use highly dimensional data of any sort to predict any trait that you're interested in that may be correlated with your highly dimensional data set. So just keep that in mind as we're going through. So just to introduce myself a little bit, I started as an assistant professor at Utah State University in July of this year. I run the small grains breeding program for Utah State University, and we work on winter barley, irrigated winter wheat, and dryland winter wheat. And we have a Instagram account that could be fun for some of you to follow, and also our website. A lot of what we work on here is related to a disease relevant to the Intermountain West in the United States. It's called dwarf bunt. It's a soil-borne fungus, and we run the screening nursery kind of as a service to the community where any of the wheat programs around the country or the world can send their material for testing in our nursery. So hyperspectral reflectance, I'll start with that. The kind of like the why and the what. This is a phenotyping workshop, so a lot of folks are already familiar with the idea that we have a phenotyping bottleneck in plant breeding. This work was done as part of my PhD at Cornell, but I spent quite a bit of time at CIMMYT during my studies, and I work with the global wheat program there. And so this is an aerial image of their largest testing station for the wheat breeding program in Ciudad Obregón, Mexico. Every year they're growing hundreds of thousands of plots, and I just like to put this photo of me in one of the plots. CIMMYT has a really outstanding staff, but they still only have maybe like 8 to 10 PhD scientists. So there's only so much ground that we can cover in terms of evaluating the material in the field. And so phenotyping can really open up a lot of doors to collect information in a breeding program of this scale. So that's kind of the why. So for the what, probably most people are familiar with the idea of reflectance off of the crop canopy and how that can be potentially useful. How do we get that information? Your basic RGB camera is doing that. It's telling you information about the red, green, and blue regions of the light spectrum, but it's not able to capture this NIR region, which contains a lot of information for distinguishing between different, conditions going on in the plant, biophysical, biochemical properties. And that's what these multispectral cameras allow us to get at. So it's getting us more narrow regions in red, green, and blue, but then it's also adding near infrared and red edge. And so a lot of groups are already working with these technologies, at least in the plant breeding community. And then what I'll be talking about today is hyperspectral reflectance. So the distinction is that this is giving us reflectance information at lots of wavelengths within the light spectrum. So it's a much higher dimensional data set compared to what you can get from multispectral reflectance, and may be able to tell us more information about what's going on in wheat. There's a wide body of literature linking grain yield in wheat to spectral indices like NDVI. And so we were kind of curious to see how we could use this information to get better predictions for grain yield. So what does hyperspectral reflectance phenotyping look like at CIMMYT? They have been doing this since 2014 or 2013. And it's actually on a manned aircraft, so it's not on a drone. These cameras are really, really expensive, so it's quite a bit safer to use it in this setting on a manned aircraft. And these are kind of some of the specs about the camera, the resolution, how many bands we got out of it. So in this data set, I was working with 62 bands. And then, we also did various radiometric calibration, atmospheric calibration, orthorectification, and georeferencing. But I'm actually not going to talk about all of these things today. I hope folks aren't too disappointed about that. This talk is more about how to use these types of data within a breeding program in a meaningful way. So that's kind of what I'll be focusing on. So what can this information tell us? First of all, it is sensitive to different growth stages in wheat. So the different colored lines here correspond to time points in which the trials were in these 3 different growth stages. So we can see, so this is for a single genotype, and we can see that there's differences in these spectral signatures depending on the growth stage. And then it also tells us differences between environments. So this is the same genotype evaluated in kind of an optimal irrigation environment and in a drought stress environment. So we can see that there's variation in the spectral reflectance signatures between environments. It also can be useful for predicting yield, because it can be correlated at different levels with yield throughout the light spectrum. you can see that depending on where you are in the spectrum, the sign changes, the strength changes. And then, of course, these correlations are also sensitive to differences in growth stage as well as environment. So the problem at hand with this data is that it can be highly dimensional. It's different than just working with a trait like plant height, days to heading, or even a few traits, because we have so many observations. In this data set, we have 62 bands, but you could have even more than that. And I like to think about this in the context of kind of what happened with molecular markers. So several years ago, when we were starting out with molecular markers, we might have one molecular marker linked to our trait of interest that we can use to make selections within a breeding program. And then as we got better at developing markers, maybe we'd have 5 markers, and we could build a multiple regression model, for example, to predict our trait and then make selections based on those predictions. But then, of course, with genotyping, now we're able to have easy access to thousands and thousands of markers. And in that situation, we now have more marker data. We have more observations of markers than we have observations of genotypes. And so it's kind of a P greater than N problem. And so the community had to kind of work towards different statistical methods to make use of all of this information, because we can't apply the same approaches that we can when we have much smaller numbers of observations. This is kind of the direction that phenotyping is going as well. Obviously, we're not to the point where we have thousands and thousands of traits, but it's kind of a similar situation. And so a few different groups have been working on this type of data, and I just want to highlight those. So this presentation is based on a paper that I worked on with Simit that was in G3 a couple years ago, but before this, that same group was working on the same data set using a few different statistical approaches to use the data to predict grain yield in wheat. So they tried different Bayesian models, different spline models, things like that. And one characteristic about those types of modeling approaches is that they can be very computationally intensive. So with this data set, we have 62 bands, but then if you think about it, we flew the plane multiple times, sometimes up to 10 times within the same environment. We flew the plane over 5 different environments that all had the same genotypes. And then we did this over 4 years. So you can see how quickly the number of traits adds up. And so that kind of adds to this computational intensive, or the intensive nature of some of these models. So I'm also not a statistician. I don't have a PhD in stats, so a lot of this stuff goes over my head. So as a breeder, I was thinking about, okay, like, what do I know how to do, and what would other breeders probably know how to do with this data? And what I settled on was the same thing that we use for genomic prediction, GBLUP. So with this approach, we're essentially calculating a relationship matrix, but instead of using markers, we're using spectral bands. And so to get this, it's just the cross product of the transpose of the spectral matrix divided by the number of bands. So that's how you get it. And it's pretty computationally efficient because you can have a large number of bands to calculate this. Obviously, people are calculating these types of matrices with tens of thousands of markers, and it's quite efficient. So this approach could handle even more information than we had in this project. And then many tools and softwares already exist to implement GBLUP that many breeders are already accustomed to. So that was kind of my idea about it. So I also wanted to mention a couple of other groups have started working in this area as well. We used a hyperspectral camera. You could use the same method with like a handheld spectroradiometer. These groups have started working with like NIRS data from a machine. So I think it was in this one, they ground up leaf tissue and put that into a NIRS machine and got the spectra for each genotype. And they also did the same thing with seeds of wheat. So it gives you the same type of data. It's just not, field observations. And they're using kind of the same approach and using NIRS. They've coined this term phenomic selection. So if you see that in the literature, they're talking about using NIRS specifically to develop kind of a relationship matrix type approach for predicting a trait of interest. So I just want to kind of give you a visual of what this looks like and how it compares to the things that we do with genomic selection. So the most basic form of a relationship matrix I suppose you could have could be the pedigree. A lot of breeding programs don't keep track of this information. CIMMYT fortunately has really deep pedigrees, but even then, pedigrees only go back so far. And so for certain pairs of lines, we don't have any information about how they're related. And then pedigrees also can't distinguish between sister lines that have the same parents. It can't pick up on Mendelian sampling. So that's another limitation. With genomics, obviously we fill in some of those holes, and we also can pick up on some of that Mendelian sampling. And then with the hyperspectral reflectance matrices, the main thing is that these are based on phenotypes. So they are dynamic. They are affected by the environment. They also capture G by E as well as the genetic main effect. So for these same 8 lines, you can see that depending on the growth stage, depending on the environment, depending on how many time points are considered, you can get different hyperspectral relationship matrices. So then when we actually put this into a prediction model, it works exactly the same way as genomic and pedigree-based prediction, but instead of your G or A matrix, we just have this hyperspectral matrix. And just to reiterate this, we can have several different hyperspectral relationship matrices depending on the time point, depending on the environment, or if you wanted, you could, combine all of this information into a single matrix. There's lots of different ways you could think about using these data. So just to summarize some of the results from that paper, here are the prediction accuracies for 2 years and 2 different environments. We have the different relationship matrices used along the bottom. G is the genomic, A is the pedigree, and then these are the hyperspectral matrices colored according to the predominant growth stage at the time of phenotyping. And what we can see is that in general, the hyperspectral matrices perform similar to, or sometimes superior to, marker and pedigree-based selection. We do have some at the early vegetative stage that aren't as helpful. And we do generally see kind of an increasing trend towards the beginning of grain filling. And that tends to be kind of the best time to do phenotyping. So before I move on, so you could use this to improve your breeding value estimation by adding a relationship matrix if you don't have any information about the pedigree or the genetic relatedness. In a prediction context, you might be wondering, okay, how could you use this? Because with GS, genomic selection, you don't have to phenotype the material that you're predicting, right? It's only been genotyped. With this, you do have to phenotype it. You have to phenotype it for hyperspectral reflectance. So if you're already doing that, you might say, well, you're already getting good yield data on it. Why would you want to invest in this? And that kind of comes back to the other project that I did at CIMMYT, which was in wheat and in many crops. There's limited seed yield per plant. And so in wheat, when we go from essentially bulk populations to derived fixed lines, we will go and sample a single spike or head from a single plant. And then we will plant that the next season, and it's called a head row, essentially. And it serves kind of as a seed increase plot, because from that single spike, we don't have enough seed to grow replicated yield trials. But we do also want to be able to make selections at that stage. It's kind of the first time we're seeing these derived lines in a row versus as a single plant in a bulk population. So if we can throw out more poor material, we'd like to be able to do that. And so with this other project, I was actually using a drone with a multispectral camera. So it wasn't quite the same technology, but it was the same idea that if we can, there are certain stages in the breeding program where we might not be able to calculate really accurate values of grain yield based on replicated yield trials, but we could do some kind of aerial phenotyping. And so if you could train a model using this type of data, and then you had your head rows where you're getting hyperspectral reflectance, but you can't get yield, you could use a prediction model to make selections. So essentially what I'm going to do today is show you how to implement this. There are two data sets that we'll be using: a grain yield data set from a CIMMYT. Well, I shouldn't have said trial because the data set has multiple trials. So it's a CIMMYT environment. And then hyperspectral reflectance of 61 bands. I took out one of the bands because it was problematic, but these were collected on 5 different dates or 5 different time points throughout the growing season. And then the goal is to be able to calculate blues and blubs for grain yield in each band. That might be a really trivial or boring activity for some people, but it's something that we have to do a lot as breeders. So I just thought I'd go over it so that you know what to do when you get raw plot data out of the trial. We'll calculate correlations between grain yield and each band. We will calculate broad sense heritability of yield in each band. And then we will calculate the hyperspectral reflectance, derive relationship matrices, and then finally perform cross-validation to determine the prediction accuracy for grain yield using these hyperspectral reflectance relationship matrices. So in case there are folks in the group that don't necessarily have a breeding background or familiarity with some of these topics, I just thought I'd kind of verbalize what we will be doing with the code before actually going through it. So a lot of times with breeding and this prediction activity, we do a 2-step analysis. You can do it in a single step, but most groups, I think, prefer to do the 2-step analysis. So the first thing that we're doing is just analyzing the field design. So when the data comes in, we have multiple replications of each genotype, and we want to eventually just have a single value for each genotype. So we need to analyze the field design. This is the model that we'll be using. So the trait will either be yield or a hyperspectral band. The genotype, the column name in the file is GID. And then there's trial, there's reps nested within trials, and then there's blocks nested within reps within trials. And then, of course, your error. And we'll be calculating blues and blubs. So in the case of blues, the genotypes or the GIDs are treated as a fixed effect. And then for the blubs, the genotypes are, or GIDs, are considered a random effect. And I'll kind of explain why we're doing both in a minute. Blub also allows us to estimate the variance components for calculating broad sense heritability. So if you're more on the phenotyping end and unfamiliar with this concept, it's essentially the proportion of the phenotypic variance that's due to genetics. And we're able to measure this because we have replication of the genotypes. So, we would assume that they have the same phenotype if they're genetically identical. But of course, there's some amount of non-genetic variation coming into play. And so that's kind of what this is getting at. It's telling us what's the proportion of the variance that's due to genetics. So we'll calculate that for yield and each one of the bands. And then to actually perform the predictions, this is again the model. And to fit this, we will use the blues for yield. The reason why we're not using blobs here is because if you calculate blobs in the first stage, essentially all the observations are shrunk towards the mean. And if you do that, and essentially if you put that in here, it's performing that shrinkage a second time. So there have been different papers that have shown how that can skew your results. So we'll be using the blues here with a random 20% set to missing. And then we will assume that the breeding values are distributed according to these different hyperspectral relationship matrices. And then to validate the predictions, we will take out the predicted values for those 20% and then correlate them to the observed blobs for yield. So that gives you a sense of the prediction accuracy. So that is everything that we're going to be doing in the R activity. And we will switch over to that. Just a reminder that the files are available. Was it online or was it, I think it was somewhere online, right?
Yeah, it's on our Google Drive. So if people want that information, it's just in the description below. There's the link where they can download everything.
Okay, great. So I will switch over to that.
Perfect. Yeah, there's no questions right now, but if you do have any questions, feel free to post them in the chat on the YouTube video and we'll pass them on to Margaret, especially as we get into the more hands-on section. We want to make sure that if you're trying to follow along, you don't get stuck.
Great. So yeah, while people are opening that up, I just want to acknowledge both CIMMYT and the NSF. So this was part of, or I was funded on an NSF graduate research, whatever that's called, GRFP from the NSF as a student working on this. And then CIMMYT was, I just really appreciate what they were doing because I think they were kind of ahead of the curve on this hyperspectral remote sensing application in plant breeding. So lots of great folks working there on remote sensing. So we'll go over to the R activity. So for this activity, you will need to install these 4 different packages. These should work on most everyone's machines. The top three are really widely used. This is one used for plant breeding quite a bit, but it's kind of old now. I hope that still works on most people's computers. And if anyone is super new to R, if you don't have these installed on your computer, you can just do install packages and then put the package that you want in quotations and run that. So we will load those. And then in this file, I've tried to just kind of annotate essentially what each section of code is going to do using words. So that's really what these comments are. So I'll kind of be describing them as we go along, but if you come back to this later, or if we're going too fast or something, just look to those to figure out what's going on, because I find that it can be really jarring to try to read somebody else's code, because we all kind of have a different style of writing code. So we'll get started. So the first file that we'll work with is the yield CSV file. So we can read that in and take a look at it using the head function. And so in this file, we have 5 columns. The first is this GID. It's the genotype. All the genotypes that CIMMYT have a different number. And then there's a column for the trial. I'll say something about that in a little bit. And then we have reps. We have 3 reps in this data set. Blocks, I think it was 5 or 6 within each rep, and then the grain yield data. So we can look at that using the histogram function. And just to explain the function or the setup of the CIMMYT trials. So this data set has 39 different trials in this trial column. Each trial contains different genotypes except for 2 repeated checks. So this is just a box plot showing the different trials. You can see that there's, significant differences between the trials. And then this just counts like the number of times each GID shows up in the data set. And we can see that these 2 were the repeated checks across all the trials. So this function, the SCR, will basically give us a little summary of the data set. And it'll tell us the type of variable that each column is coming in as. And so when we read it in, GID, rep, and block are all coming up as integers, and the trial is a character variable. But to fit these in a model to analyze the field design, these need to be categorical variables instead of the model trying to fit like a linear regression to the GID or something like that. So we can use the factor function to change these variables to categorical variables. I'll just start running this right away and then explain it because it will take a little bit of time. So this is that model that you saw in the PowerPoint to analyze the field design. This will give us the blues for grain yield. This is a function available from the LME4 package that allows us to fit random effects. In this model, as I mentioned before, the genotype or the GID is set as a fixed effect, and then the other 3 are set as random effects. And to get that random effect in the LME4 notation, you just do this 1 and then vertical line, and then the name of the column. And to nest variables within other variables, you can use this colon. And I believe the order that you have them in doesn't really matter. So we have rep nested within trial, and then block nested within rep within trial. So that is still running. Yeah.
We have a question, and I think this might be a good time to address it, and I'll read it to you. This question asks, if you don't have replication, how can we do this analysis because some of the breeding programs don't have replication? So can you describe how you would integrate that if you can?
Yeah, that's a good question. And it comes up a lot because it's something that I have a problem with in my breeding program too. We're a really small breeding program. We have limited resources. And so it's tempting to implement an unreplicated design because it allows me to grow a larger number of genotypes, right? And my PhD advisor at Cornell did this. There are designs that have been developed for this. And generally, they are based on the replication of check varieties widely throughout the trial. So the main one that I'm most familiar with is the augmented design. And in those designs, you can fit another model where you're essentially trying to correct the observations based on information about the checks. So the checks are essentially capturing like the spatial variation in the field. And I know for that one, because I always struggled figuring out how to analyze the augmented design in R, there's a good YouTube video on that. I can't remember if it was from Ohio State or something like that, that shows you how to analyze an augmented design. And so it is possible to work with unreplicated data for this type of analysis.
Great.
So I
thanks.
hope that answered the question. Okay, but that was great because it gave us time for the model to finish. I hope everyone has finished, but I'll continue to go kind of slow in case it's still working on your computer. This fixed F function will return the fixed effects from the model. So if we look at the first 10, it's set up as like a vector. And then these are the names of each of the entries of the vector. And we can see that the first one is the intercept. So let's just take that out by taking the first one, putting it into this variable called yield.int. So there it is. And we can add the intercept to all of the blues to center the blues around the mean. The other thing to know about the intercept is that it's actually also represents like the first GID. It's the value of the first GID is kind of used as the reference, and then everything is with respect to that, plus or minus. So we can add the intercept to all the other blues except for the first one, of course. And then, as I mentioned, this is a vector with names. So we'll want to take these out and put this into a nicer format, essentially. So put it into a data frame where we have a column for GID and a column for the blue for yield. So if we look at the names, the first one is intercept. So we need to change that to the correct GID, which is the first level of GIDs in the yield data set. So we'll do that first. And then we want to take off this kind of annoying character string that got added, GID. So this G sub function, you can basically tell it what character string to look for and what to replace it with. So if we run this, it basically takes off those GIDs, and we can replace the names with the corrected version. So now when we look at the vector, we have all the blues in the vector, and then the names are the GIDs. And we will put those into a data frame where we have a column for the GID and a column for the blues, which we'll call grain.yield.blue. And if we look at that, that's what it looks like now. There's probably some faster, more efficient way to do that that I'm not familiar with, but that's what we're going with for now. And then if we looked at a histogram of the yield blues, that's what we have now. And of course, we now have one value for each genotype that we can use in our prediction model. For calculating Blubs, it's essentially the same model as before, but now we're changing the GID from a fixed effect to a random effect. So we're just putting that 1 and the vertical line in front of the GID variable, and we can run that. That goes a lot faster. And the ranF function this time returns the random effects. So if we run that, it returns a lot of stuff. That's because we have multiple random effects. So if we want to just get out the GIDs, we can just use the $ and GID to print just the ones from the GIDs. And so in this model, we had no fixed effects other than the intercept. So if we run that fixed F function from before, it will just show us the intercept. And as with the blues, we can center the blobs around the mean by adding the intercept. So we'll put that into a variable called yield.blubs and take a look at that. And as with the blues, we want to put a column for the GIDs in there. We can see that the way that this is printed out from LNER, the GIDs are actually listed as the row names. So we'll just use the row name function to get those, put them into the data frame. We'll call that column grain.yield.blub, and then we have the blubs. So similar to what we did for blues. And if we look at the histogram of the blubs, there they are. As I mentioned with the blub model, that allows us to partition out the variance, and we can get the genetic variance and error variance, which is what we need to calculate broad sense heritability, which once again is the proportion of the phenotypic variation that is due to genetics. So to get that information, first we can just use summary, and that will tell us like various information about the model. And it actually does show us the variance components here. But the annoying thing is, as far as I know, and maybe somebody else knows a better way to do this, but as far as I know, you can't pull these out of summary. You have to use this other function called var core with a capital V and capital C. And if we look at that, unfortunately, that really doesn't even have the variance components. It's just showing the standard deviation. But for reasons I don't really understand, if you put that into a data frame function, it will expand and give you this larger data frame, which now has the variance components, which we saw in the summary from before. So that's how we can pull them out. We can essentially use that $ to take out the V cove column. And then we want the first and the fifth ones, which correspond to the GID and the residual. So we get our genetic variance and our error variance. And then this is that model for broad sense heritability that I showed in the PowerPoint. So it's the genetic variance divided by the sum of the genetic variance and the error variance divided by the number of reps, which was 3. So if we run that, we see that it's pretty high. CIMMYT generally gets pretty high broad sense heritability for a grain yield because they have, it's just a really uniform environment in Oregon. There's a lot of replication, and they do a really good job with just trial management and everything. So that's kind of all we're doing with the yield data for now. And we'll move on to the spectral data, which can be found in the other file, PhenomeForce_Spectra. So we'll read that in the same way as before into a variable called Spectra. And we can use this view function to just look at it. So with this, the first 4 columns are the same as those that we saw in the yield data set, GID, trial, rep, and block. But then it has this additional column for date. And that actually shows you the date that the plane was flown to capture the hyperspectral reflectance data. And so we see that there are like multiple observations for this GID in this trial, in this rep, in this block. And it's because we evaluated it at different time points. So there are 5 different dates in here. And then the rest of the columns are the hyperspectral bands, and they have like a band number, so B, 2, 3, 4, etc. And then the number after the period is the wavelength. So where in the light spectrum that band is coming from. So that's how that is set up. And as with the yield data set, we need to change, if we look at the structure of this data frame, we need to change the GID, trial, rep, block, and now the date to factors. So we'll do that. Now they're categorical variables. And I just want to, before we dig into anything, visualize the data for a single genotype. It's kind of a lot of finagling to get out the observation for one genotype in the way that we want it to visualize it. So that's really what a lot of this code is. So I'm just taking out the spectral data for this one GID. And if we look at that, it's like all the different reps and then all the different dates. And we'll use this melt function. So what this does is it'll take the columns containing the spectral values and put them into like individual rows. So instead of having this wide data frame, you have a really long data frame. It kind of renames the columns, so we'll call those band and reflectance. And then to plot the data according to the wavelength, we need to take this B, the band label, off and just get out the number. So we'll do this a bunch of different times in the code. So first we just convert it to a character. And then this line of code will just take off the band number. And we're left with just this, all the numbers of the wavelengths. And then since the field design has not yet been analyzed, we still have 3 observations for this genotype. So we'll just take out the first rep and put that into ggplot. And so the x-axis will be the band, the y-axis will be the reflectance. And then because we have different dates, we'll set the color to date so that it prints like a different line for each date. So if we do that, we get this, this plot, and we can see that the reflectance for this one genotype in this one plot changes throughout the season. So it kind of starts out at the highest in the near infrared region and then kind of decreases, and then this is closer to senescence. So that's essentially what it looks like. That's the data for one plot at one time point. It's 61 observations. So we're going to do the same thing that we did for yield with Blubs and heritability, but it's a little bit more complicated now because we have multiple dates. So there's lots of different ways that you could do this. You could also calculate a blub using all the dates together, putting date in the model. But for this, we will analyze the dates separately. And the easiest way to do this, in my opinion, is to just create a list where we have 5 different matrices that are, the same format, but they have the spectral data from the different dates. So if we look at the levels of date, these are the 5 different dates. And to start out, we'll just make an empty list of length 5. So that's our empty list. And then we'll pull out the spectral data from each date one by one and put them into this list. And then to keep track of which date is going where, we can just name each entry of the list as the date. So that's what that is doing. So when we do that, we can use the view function to look at what that looks like. And now it's showing us that we have these 5 different data frames in the list, and they're all the same dimensions. And essentially the only difference is they are the information from the different dates. So now, we only have 3 observations for each genotype, depending on according to the 3 replicates. So that just makes it a little bit easier to work with. We are now going to calculate the Blubs and the broad sense heritability for each band on each date. And again, there are a number of ways that you could store the data, but what we will do is kind of create a data frame to store the band heritability. So if we look at the bands, we have all these different bands. And then if we look at the dates, we have these 5 dates. We can create a data frame containing each combination of those using this expand grid function. And then it has one column with the bands and the other column with the date, and it has all of the combinations of them. We'll give them the appropriate column names, and we'll create a new empty column for the broad sense heritability. So again, there are different ways that you can do that, but that's what we'll work with for now. And then we'll create another list with a length of 5 to store the blobs for the bands from all the different dates. So we'll create that list. Now we have this empty list. And just to get started and make our life easier later on, within each entry of the list, we'll put a data frame with one column, which is the GIDs. So that's what this is doing. Then if we look at like the first one in there, it's just got this one column with the GIDs. So as before, we want to keep track of the appropriate dates. So we'll give the list some names. And then this loop is going to do a bunch of stuff. So I'm just going to start it right now and then go through it. So it'll go through the list one by one, and then within each element of the list, it will go through the bands one by one. So first I'm taking out the correct, the data frame for the correct date and putting it into this temporary variable. And then I'm taking out just the column names for the trial design and then the correct band that we want to look at one at a time. And I'll just rename that column reflectance. And so then we have this little data frame with just the information that we need for calculating the blobs for that band. So that model should look very familiar at this point. All we've changed really is we've gone from yield to reflectance. And so right now it's fitting all those different models. You're seeing these errors because some of the bands have no heritability, or one of the variables has no effect. But for now, we'll just ignore that. But you would have to deal with that in some way. And then we extract the variance components as we did before to calculate the heritability. And then we'll store that in this bands data frame that we created before, matching the band and the date to the correct band and date. And then we'll get the blubs out in the same way that we did for yield, by adding the intercept to the random effects, putting it into a data frame with the GIDs, and then we'll merge that into that starter data frame that we made that just had the GIDs. And then I just like to put a little counter to see how far along we are. So that finished running, and if we look at that, we have still our 5 data frames, but now they're full of data. So we have a GID column, and then these are the blobs for each band. And that's what all of these look like. They're just from the different dates.
Margaret, we do have a question. Is this a good time?
Yeah.
Okay, so someone was wondering why the spectral reflectance values in your CSVs are greater than 100. Maybe you could just clarify the units in your reflectance?
Yeah, I thought I was going to get that question. And I was trying to figure that out before this presentation. But I don't actually know. I think that, it might have something to do with the way that they were calibrated, which was done by the remote sensing group at CIMMYT, so I don't have all the information about that. So yeah, I'm sorry, I can't really answer that question.
That's okay, thank you.
But they are heritable, so they're not just totally Yeah, totally random. So yeah. So if we look at the bands data set, we have each band and then the date for the flight that it corresponds to, and then the broad sense heritability. And we'll want to visualize those. So as before, we need to take out the wavelength number from that band label. So this is the same script to do that. And so we have this new column called wavelength, which has the numeric values for the bands. And then we can run a pretty simple ggplot script to plot the broad sense heritability against the wavelengths, and we can set the color to the date so that each date has a different line. And so this is what it looks like for these 5 dates. What I saw in general, regardless of the environment, the year, all of those things, the beginning of the lowest values wavelengths generally had lower broad sense heritabilities. And then as you get closer to senescence, we also saw a decrease in the heritability of the bands. So those are just some general observations from the full analysis of all the different environments and everything. So I want to just look at the spectral data for a single genotype. So we'll do that again. It's sort of this, it's essentially the same thing that we did before. So I won't like go into great detail with all these lines of code. So these are the blobs for our single genotype now. And then I also want to show like what it looks like for multiple genotypes. But just so that it doesn't get too busy, I'll plot multiple genotypes on a that should say single date. And so I'll take out the first 15 genotypes from the first date and kind of do the same thing again. And then this time the color is the GID. And so that's kind of what it looks like. There's generally more variation or just a wider range in the near infrared region. So the next thing we can do is calculate the correlations between grain yield and each hyperspectral band on each date. We'll create a data frame to do this, where we have a column of the bands, so that each band will have a correlation. And so to calculate the correlations, we will first merge the yield data with the blubs, the full blub matrix from a single date. And then using the apply function, we can calculate the correlation with all the columns. And then we'll store those in a temporary data frame. And then we will merge them with this data frame that we just created. And the column name will be the date. So that's what's going to happen when we run this. So now we have this data frame with the bands and the correlations with yield from each date. To plot those, we have to kind of do the same thing again. Putting it into that long form, putting on the wavelength column. So now each band on each date has a correlation in its own row, and then we have the wavelength. So if we look at this, we can see that the correlations with yield, I kind of showed this in the PowerPoint, the sign changes depending on the point in the light spectrum, and then also the date. So we can see how those correlations in general get weaker with that time point that's closer to senescence. And this kind of varies widely depending on the environment and the time point and everything. It's kind of hard to decipher any kind of biological explanation for the variation in these, but perhaps that's a project for somebody. So next we will prepare a relationship matrix using the hyperspectral bands from each date. So we will again create an empty list with the names as the dates. So we have this empty list. And I showed the equation for this before. So like first we scale the bands, and then we take the cross product of the transpose matrix and divide by the number of bands. And that just gives you the matrix. It'll put it in there, and we'll give the appropriate row names and column names for the GIDs as well. And so if we want to look at the first one, just like the first 10 rows and columns, it looks kind of like a, like a relationship matrix. So, so I just also want to visualize this. So, but I don't want to use the whole thing because it would be really big and hard for R. So we'll just take the first 100 rows and columns, kind of do the same thing that we've been doing. And then that's kind of what you get. So you can see which genotypes are more or less related, as you would with a pedigree or a genomic relationship matrix. And then really the last thing is to do the prediction modeling and cross-validation. So to prepare to do that, the same thing that we've been doing again, creating that empty list with the names as the dates. And then I'll just start running this. So what this is going to do is it'll go through the list of relationship matrices. And I want to set the seed here so that when we do subsampling to get the random sample, we get like the same samples for all the different dates. And so then once we're working with a single date, I'll just do 10 iterations of prediction. You can do more or less, depending on how fast your computer's going. So to do this, we will put the yield blues, again, these are the blues, into a temporary variable. And then we'll take a random sample of 20% of them and set those to missing. And then there's a bunch of different like softwares or packages to do mixed models where you can give it like a covariance matrix. And I usually use ASReml myself, but since that's proprietary, I'm just using this kinblub function from rblub, and the K is the spectral relationship matrix for the given date. And so then when that finishes, it'll have a column called pred. Those are the predictions. We'll put those into a data frame with the correct GID. We can merge this with the yield blubs in order to validate the predictions. And to do the correlation, we only want to consider the ones that were, because we'll get the predictions for all the genotypes, but we only want to consider the ones that were set to missing. So that's what this is doing. It's taking out just the ones that were set to missing. And then this last line is basically adding the Pearson's correlation between the observed blub and the prediction to a list. So it's still going. So when this finishes, each list entry for the 5 different dates should have 10 prediction accuracies based on different subsampling, and but all the dates should have the same like subsampling scheme. So that is eventually what we'll get out of this. And then really the last thing that I have is to visualize this. So we're kind of doing the same thing as before. And then we'll show box plots of the prediction accuracies where each box plot is a different date. So while this is wrapping up, like I'll just talk about different applications of this. As I mentioned at the very beginning, this is in the context of aerial hyperspectral reflectance, wheat grain yield, and yeah, I guess that's it. But you could use this approach using any highly dimensional phenotypic data set that you have. Maybe like an ionomics data set or something like that. And then it could be for other traits as well. And then with this data set, a challenge was that the trials at CIMMYT are often, they're not planted on the same day, and then they're irrigated differently to simulate different growing conditions, like a severe drought, a moderate drought, like a heat environment by planting it late in the season. But because we were working with a commercial pilot, we essentially just had to call him up and he would fly over the whole thing. So we couldn't really just have him come whenever we wanted to phenotype different environments when they were right at the perfect growth stage. So the data set that we got was kind of all over the place in terms of like which phenological stage the plants were at. And, you know, that's a problem that comes up with a lot of aerial phenotyping approaches. And what we chose to do to deal with that was just basically calculate blubs for each growth stage. So regardless of how many time points we had, we just defined growth stages based on the days to heading data that we had taken. and then however many time points we had within that stage, we use all of those to fit a blub for that particular time or that particular growth stage. So that's how we dealt with like predicting across environments, but there are probably lots of different ways that you could do that and possibly much better ways to do that. So this has finished running. So as I mentioned, we have the 5 list entries from the different dates, and each one has 10 prediction accuracies from the 10 iterations. And so we can plot those, and we see that they kind of increase. So that was probably that increase as we get close to the beginning of the grain filling period. And then the state that was closer to senescence had a much lower prediction accuracy. So this is how you can test prediction accuracy and use this type of data. How do I get out of this? So I'm happy to take questions on any of the R stuff right now, if there are any.
Margaret, we had a question about some the data quality.
Mm-hmm.
Just a comment on some of the shapes, and maybe we can hear if you had some ideas about it. So the question was, there are lots of unexpected bumps over 700 nanometers in the overall hyperspectral data. Any comment on the data quality? I believe it would not be a calibration issue or sensor-related noise. So I was kind of looking back at some, I think it seemed like for some of your genotypes, like it was like there were smooth curves at lower bands, and then at higher bands, there seemed to be, I think you'd have to go back several plots.
Like back here.
Yeah, or even, I'm looking at one of your very first ones because I started to follow along, and I'm not sure if that's the one. I didn't, yeah, probably go forward one. That. Perhaps that's what they're referring to. So if you had any comments on that.
These are the heritability data. So I don't know if the comment was like specifically in relation to that. What I can say about that is it might be an artifact, and I'd have to look. It might be an artifact of just like, you know, these data are continuous, but because we did like downsampling, it could be just that these bands ended up being like further apart. So that's why you might see that there's more drastic change, because we didn't have something like in the middle measuring it to make it smoother. So that could be it. It's true that it, you know, there's a good chance it could be something to do with the sensor. What I can say, I'm not like a remote sensing expert, so I can't really comment too much on like why this would be happening, but just from like analysis of the breeding of the data for breeding from that perspective. One thing that one of the other papers did was they tested removing bands based on heritability. So yeah, I think that they were taking out bands that had heritabilities lower than a certain, maybe it was 0.5 or something, to test whether or not that could improve your prediction. So kind of like a data quality quality control type of thing. And I think they found that it helped in certain environments, but not really others. But I just want to bring that up because that's something that you can do with this data. And because again, like it can be when you have such a high volume of data, and I think that was part of the challenge for me, is that I kind of got bogged down by having 10 flights in 5 environments across 4 years. So I didn't like spend as much time actually, trying to figure out, like go back and figure out what happened with certain parts of the spectrum and that kind of thing. But I just want to bring that up because that's, the QC part of it is something that you can do if you're concerned about data quality issues. Another thing that I'll say about that is, like, from a breeding perspective, a lot of times people want to have a really nice biological explanation for everything. But with breeding, I guess I view it as more of kind of a black box where I'm not really worried about like certain or the way that the data looks and why it looks that way. I'm more interested in how it predicts, I would say. So that might be a dissatisfying answer for some people, but
it's still a good answer, right? Like, not everything is going to be perfect, but if it's predictive, that's still quite important, right? That's what we're looking for.
Yeah, that's the point. That's the main point. Thanks for summarizing it a lot better than I did.
Great.
Yeah.
Jennifer or Max, did you have any questions you'd like to ask?
Yeah, I do. Margaret, that was just fantastic. I love having a workflow that I can go through and learn from. That was just a fantastic workshop. My question is a little bit more broad. It doesn't directly relate to what we talked about today, but so, for those of us that don't have access to this awesome hyperspectral sensor, maybe we could have access to like a 5-band sensor or a 10-band sensor. Like, how translatable are those things? Do you think that's? Do you think there's a lot more we can extract out of the hyperspectral space than the 5 or 10-band space? Do you have like any thoughts on that?
That's a great question. There's a lot that I can say about that. So one of the other papers that used this data set did compare like using all the bands against more common vegetation indices. And they did find that there was an improvement in prediction accuracy. So there does seem to be value in using all of the bands as opposed to like just trying to calculate vegetation indices. But I do understand that a lot of people don't have access to this data. If you do have, a more reasonable number of bands, another approach that you could take is like a multivariate prediction approach. A good paper for that was one from Jessica Rakoski from it was also a CIMMIT data set where they it's essentially adding the HTP traits along the Y side of the equation. And it takes advantage of the genetic correlation between the HTP trait and the trait of interest. And so if you have, again, it's a similar situation where if you have that data but you don't have yield, you can use it to improve GS models, essentially. And I wanted to put in a little plug. I don't want to jump the gun too much, but we are going to have a workshop on how to do that type of stuff here at Utah State over President's Day weekend. So we're bringing in Kevin Wong from University of Florida, who was working in Jesse Pullen's program before he left. And then Jessica will be coming in. And so we will go through essentially step-by-step how to deploy a UAV with a camera, how to stitch all of the images. And then on the last day, Jessica will talk about some of those multivariate approaches for using those types of data in selection models. So I can send that information to PhenomeForce when it's available. The last thing I did want to say about that is I think you could still try like the relationship matrix approach, even if you only have a multispectral sensor. But if you have multiple time points, you know, that increases the dimensionality of your data. And I think that would be a really interesting area to see if using a multispectral camera just with multiple time points could be useful in this same modeling approach.
Awesome. Thank you.
So I wanted to thank you for using RR Blub as the alternative for ASRML today. So thanks for including that. I've tested a few different options, so I was really glad to see that. And along that line, we have a comment that maybe I think you'll like answering this question. So it is, can you elaborate more on the linear mixed effect models that you used? Why did you choose this model, and what is its advantages compared with some regression-based models such as linear regression?
Yeah, well, I think it comes back to what I was talking about with like the dimensionality of the data and genetic markers, where once we got good enough at genotyping, we were able to recover thousands and thousands of markers. And in those situations, we can't just use like a multiple regression approach because we don't have enough observations to use that type of modeling approach. Obviously, like with the data set that we use today, we had far fewer bands than we had yield observations. So it's not really the same problem. But, you know, let's say we added all of the time points together in a large matrix and tried to analyze it like that. In that situation, you would get closer to that problem of having fewer observations than you have bands. So that's kind of why we were interested in going in this direction. But certainly there are tons and tons of different options for analyzing this type of data, you know, from linear regression to like non-parametric models, machine learning. And so I think data sets like this really provide a lot of opportunities for looking at different modeling approaches and comparing different modeling approaches. There are probably other approaches that give higher accuracies than this with these data sets. I think that from my perspective, I mean, I don't want to like promote it as the best method or anything like that, because I don't necessarily think that it is, but I think for breeders, it's something that like a lot of folks would be able to understand and implement themselves, just based on like where everybody's skill sets are. And it's also, as I said, like something that they would have more of the time to implement versus, you know, trying to compare a lot of different models that are maybe have fewer softwares available, have fewer training resources available, etc. So.
Great answer, Margaret. So, Jennifer, Max, do you have any more questions, or do you think we've grilled Margaret enough?
Great job, Margaret.
Yeah, that was a great
Thank you.
presentation.
I hope that this was useful for people.
I think that our viewers will really enjoy how in detail you went when you went through all of your R script. That was very helpful. So if that's the case, then I will just take this chance to plug our upcoming PhenomeForce talks. So of course today we had Margaret's talk, but upcoming we have one more Drone to Phenome and PhenomeForce joint presentation. So next week we're going to have our last of the series, which will be looking at an automated approach for spatial cropping and plot identification of hyperspectral aerial imagery used in small plot and on-farm research, presented by C. Yang and Tyler Nigon. So that'll be again next week at 10 a.m. Central Time. So same YouTube channel. If you're not already registered to get the emails, there's a registration link in the description. And if you add your email there, we'll send you the materials we have, like Margaret's R scripts and CSVs. We send those out the night before so you can follow along. So make sure to be there. And if you're interested in becoming more involved with the PhenomeForce community, or if you'd like to give a presentation in a future series, please make sure to reach out to us at phenomeforce@gmail.com and subscribe to the YouTube channel, because we're going to do our best to keep putting out content like this for everyone to be able to learn more about phenomics. So yeah. Thank you everyone for coming out, and thanks to the co-hosts and of course Margaret for your talk today. We super appreciate it, and we'll be back next time.